The law of conservation of matter is related to balancing equations. So after this section, you should be able to describe the law of conservation of matter, explain how the law of conservation of matter is represented in an equation, and determine the ratio in a balanced equation. The law of conservation of matter states that matter cannot be created nor destroyed. And we'll add a little bit to this. We're going to say it can be rearranged. So if I have atoms of element X, the gray spheres, and they add to atoms of element Y, the red spheres, you'll notice that we get a new compound of XY. And so the matter is in a different form, but we still should have the same amount of red and gray spheres before and afterwards. And so we're going to use balancing equations to represent this. In a reaction, your reactants must equal your products. This concept is represented by a balanced equation in order to show that when reactants form into products, nothing is lost or gained, only rearranged. So for example, if I have two different compounds in an Erlenmeyer flask, notice the mass, 300.23 grams. If I were to mix those compounds together, then I'll end up with a new compound, but notice the mass does not change. Everything remains equal, only transformed. And here's a little video to supplement. So now let's look at how to balance an equation. First of all, you never ever change subscripts. The subscripts, which are the little numbers at the bottom, is what identifies how many elements of each must be in the compound. If you change the subscripts, you change the identity of the substance, which is a big no-no. For example, if I had water, H2O, and I changed one of the subscripts, perhaps if I changed it to H2O2, by adding this 2 right here, I have changed it from water to hydrogen peroxide. And hydrogen peroxide will not quench your thirst quite like water will. So changing subscripts, you don't want to do it because it literally will change what your substance is. A coefficient, however, can be added in the front of a compound to alter the amount of the substance. So by coefficients, we mean these big numbers in the front. For example, a 2 in front of aluminum sulfate doubles the amount of the entire compound. So here I have 2 aluminums, I have 3 sulfurs, and I have 3 times 4 is 12 oxygens. By putting a 2 in front, I am doubling. It distributes to everything that I have. So I'll have 2 times 2 equals 4 aluminums. 3 times 2 is 6 sulfur. 3 times 4 is 12, times 2 is 24 oxygen. And as you can see, it's exactly double from what it was before. Each element you should have twice the amount. So coefficients distribute across the entire compound. Pre-balancing checklist. You need to make sure that your diatomics are accounted for, and you should make sure that your flip-flops, your charges, have been canceled and switched properly. So our first example is aluminum carbonate will yield aluminum oxide plus carbon dioxide. We have to translate this first. So aluminum is Al plus 3, carbonate is CO3 minus 2. So when I switch the charges, I need 2 aluminums and I need 3 carbonates, which will yield aluminum, which is plus 3, and oxide, which is a minus 2. So when I switch those charges, I'll have Al2O3 plus carbon dioxide, which is covalent, and so it's just 1 carbon, and di means 2 oxygens. And so now I am free to balance the equation. Here on the left side, remember this is our dividing line, on the left side I have 2 aluminums, and on the right side I have 2 aluminums. So at the moment that's already balanced. Now I'll do carbon. The general rule is you want to save oxygens and hydrogens for last. So we don't want to do oxygen just yet. So carbon, here I have 3 carbons when I distribute this 3. So there are 3 carbons. And on the right side I only at the moment have 1 carbon. So in order to fix this, I'm going to add a 3, a coefficient of 3 in front, which is going to distribute to each of these. Now I have 3 carbons on the right hand side. On the left I have 3 times 3 is 9 oxygens. So I'm going to just kind of jot that down right here. 9 oxygens on the left. And then I have 3 here plus 3 times 2 makes 6, which equals 9 oxygens on the right. So I do have my 9 oxygens on the left and I have 9 oxygens on the right. So since I have an equal number of each type of atom on both sides of the equation, my balancing is complete. So my final answer is going to be Al2CO33 yields Al2O3 plus 3 CO2. There is what's called a mole-to-mole ratio in this problem. The mole-to-mole ratio across this equation is 1 to 1 to 3. So I would say I have a 1 to 1 to 3 mole-to-mole ratio in this equation. There's an understood 1, an understood 1, and a 3. All right, let's see another example. Nitrogen gas plus oxygen gas yields dinitrogen pentoxide gas. So nitrogen gas is one of my diatomics. So it's not just N, it's going to be N2. Plus oxygen gas, which is another diatomic, it's not just O, it's O2, is going to yield di means I need 2 nitrogens, and pent means I need 5 oxygens. So let's balance this. On the left side I have 2 nitrogens, and on the right side I have 2 nitrogens. On the left side I have 2 oxygens, and on the right side I have 5 oxygens. So here's my issue with the oxygens. In order to balance them, you want to use a common factor. So if I do 2 times 5, 10 oxygens would be the choice for each side. So on the left I need a 5 because 5 times 2 will make 10. And on the right I'll put a 2 in front. 2 times 5 makes 10. So now I have 10 oxygens on both sides of my equation, which is what I wanted. My nitrogens have changed. Because I added this 2, that changes my nitrogen now to 4 nitrogens. So this is no longer 2, it's now 4 nitrogens. So on the left, I'll need a 2 here. 2 times 2 will make 4 nitrogens. So because I have 4 and 4, 10 and 10, I've now completed this balancing. The ratio is a 2 to 5 to 2 ratio. And in our next video, part 2, we'll see several more examples of balancing an equation.